What's up, everybody? This is part 2 of a lambda-calculus compiler in F# series. In part 1, we have defined the basic structure of the language and, again, a basic tree-walking interpreter that uses substitution to reduce the terms of the language. It's simple, but it is slow. So today we're going to improve the tree-walking interpreter, make it more mature, more performant, not that much more complicated. And to do this, we will introduce closures, environments, and we'll also extend the language with let bindings, including recursive let bindings, so that we can define recursive functions in direct style without using of a fixed point combinator. So if this sounds like fun, please keep watching. All right, let's start with a quick recap. Previously, we have defined the AST of our programming language. That's the expression type here. And it is basically a lambda-calculus with some extensions like literals, built-in operations, and conditionals. We have also defined the evaluation function, which takes an expression and returns a simplified or reduced expression. So basically it takes an expression and tries to simplify it as much as it can. Or it may also raise an error if we try to do something nonsensical like adding 42 to a lambda. And the code of this interpreter is actually very straightforward. There is not that much we can optimize except this part where we're applying a lambda to an argument. And the main complexity is in this substitution function. So if we have something like lambda x plus 1 applied to 5, what we need to do to evaluate this application, we need to take this syntax tree, this AST, and we need to replace all three occurrences of a variable with name x with another node, which is going to be a literal of built-in type int with value 5. So we need to do tree rewriting. And this is pretty expensive. That's why the interpreter is pretty slow, as we have seen the last time. So one way to improve this is try to avoid this explicit substitution when evaluating the application. So instead of kind of rewriting trees to evaluate the application, we could instead just record the fact somewhere that name x now is mapped to value 5 for the evaluation of this expression, right? So basically we introduce the notion of the environment, which is a mapping from names to values. And we use this environment to evaluate the expressions. So for instance, in this case, we start with an empty environment, right? And we try to evaluate this thing 5. So what's going to happen next is kind of to do this application, we modify the environment. So we add this mapping of x to 5, and we want to evaluate x plus 1. So what happens next is we need to look up the value of variable x. And to do this, we take a look at the environment, we find the mapping, and we use the value from there to have 5 plus 1 and then 6. So kind of that's the basic idea. We will have some gotchas when evaluating lambdas, but we will kind of discuss this in more detail when we actually start writing evaluation for the abstraction and etc. Cool. So to proceed, we will need to change the semantics of the evaluation function from kind of term reduction to evaluation to some concrete values. And so we need to introduce the notion of a value. So let's do this. And the value can be either an int, or it can be probably something else. And this something else will be called closure. And why it will be called closure, we will see a little bit later. But for now, let's leave it like this. Let's also use this thing. Cool. So let's then change the evaluation to return value. And then let's start changing the code. All right. So here, when we evaluate arithmetic and comparison, previously we were kind of casting the expression to an integer literal. Now we wanna cast value to a value literal. So we are going to kind of massage this module a little bit. First of all, we're going to get rid of this. We will not need substitution anymore. Then we need to make this function operates on values. And we also need to change the types here. We don't need this, at least for now. Cool. So then we do the arithmetic function, apply, and then we wrap it into an int value. Okay, so far so good. And then we do the comparison. In the conditional, this is also like everything is pretty mechanical. So now the interesting bits. So let's start with variable first. As we have discussed, we need to introduce the notion of the environment. Let's do this. So we have the value. And our environment will be a map from variable name to value. All right, so far so good. So if we go down here, we also need to introduce their environment argument here. All right, so when we evaluate the variable, we are going to look up name inside our environment. And basically, if we find one, that's fine. if we don't have anything, so we get an empty option as a result, we'll need just to raise an exception. So we can do this with this default with and here we will just raise an evaluation exception, and let's add another thing here. So let's call it unbound name. Okay, that's probably enough. Okay, cool. Wow. So now the most complicated bits. Let's start with the abstraction. So first I wanna deconstruct the fields. So we have the variable and the body of our lambda abstraction. And the question is, what will be the value? Right, so we do not try to go inside lambda body and simplify it, but we cannot just return the body as is. So we need some way to represent this lambda as a value. We have ints, we need something else. And I guess like one motivating example here is the evaluation of this kind of a lambda within lambda, right? So when we have something like lambda x that has lambda y inside that returns x plus y, and we apply it to 5, we get basically a partial application of this function of 2 arguments. And so what we will have as a result is another function that has x plus y inside, but also together with the fact that x is bound to 5 inside for the purposes of evaluation of this lambda. So basically, this combination of the environment together with the some expression that needs to be evaluated with this environment is called a closure. So let's introduce the closure type. So we go here and we add closure of closure, and the closure itself will be as I said, basically a record with environment with a variable and the body, which is just an expression. Cool. So now we can go back down here, and the evaluation will return the closure. So the environment cool. Now the application part. Right, so we need another function that will take a value and try to cast it to a closure. So let's implement it. Okay. and let's deconstruct it right away.
Cool.
So we evaluate the expression, we make sure it's a closure, we have parts of this closure, and then we evaluate the argument using the same environment we used to evaluate the closure. And then the interesting bit is this. We need to construct a new environment for the evaluation of the closure body, where variable is associated to value to the argument value. So let's do this. Basically, we add a mapping from closure var to arg value into closure env. And then what we do, we evaluate closure body in the new environment. So I think this looks fine. Let's remove these comments. Okay. So let's see if it works. We need to provide an empty environment for the evaluation of the expression. So hopefully now it's going to be fine. Woohoo! Looks like it actually works. Interestingly, I think previously the Fibonacci of 30 was taken 17 seconds. Now it's just 3 seconds. So it's like 5 times faster. Not bad, not bad at all. So let's see what will happen if we run it with the release build. All right, so it takes just 1.3 seconds to evaluate the Fibonacci of 30. That's, I think, is a pretty good improvement, given that the code is, I think it's actually simpler in a way, because we don't have to have the substitution and stuff. So yeah, probably simpler code, 3 times better performance. That's looks good to me. So what we are going to do next is we will introduce bindings to the language. So if we take a look at the Fibonacci here, so we had to apply the fixed point operator to this fib step function, just to refer to the name of the function and invoke it recursively. This is very cumbersome, and we can do much better than this. Let's extend the AST. We need a new type of node, which is called bind, and binds can be either recursive or non-recursive. So bindings can have basically it's a first part is the name, second part is the body of the bind, some expression, and then we have the kind of continuation, which is another expression. So for instance, if we have something like let x equals 5 in x plus 1, it is a non-recursive binding. The variable is x, the body is expression 5, and the expression is variable x plus 1. So that's the idea. Now we need to go here and add a code to handle this. So we have the bind. Let's deconstruct it. So when it comes to non-recursive bindings, that's pretty easy. So let's kind of handle this first. Let's evaluate the body. Then when we have the body value, we construct a new environment for the expression. So we add the binding from variable to body val. Then we just evaluate the expression using this new environment. This part is pretty easy, but what do we do if we have a recursive binding? So the example that we use is the Fibonacci function. So basically it's something like this. So to evaluate the body of the binding, we need to have this name associated with the value of this body. So we need a recursive thing inside our environment, right? So inside our environment, we have a name that is associated with the value that has this name that is associated with itself. So this is pretty mind-bending, and it's also not really clear what to do with something like this. So let's say in this situation, this recursive binding is well formed, right? So we can evaluate the body without going into an infinite loop. So we just an abstraction. So what I mean is that if we have something like this, is a bad recursive binding, because in the body it refers to itself and it is not evaluated. So this is a bad thing to have in your program. Here the name is kind of accessed via a lambda indirection. This type of recursive bindings are fine, and ideally we would need to detect these bad bindings and do something with them. So one way to handle this is to see. So let's define the new thing called body env. That's the environment that we will use to evaluate the body of the lead binding. So if, I guess, the non-recursive part is pretty straightforward, then we just return env. Else we need to construct a new environment, and let's add something like let's add a mapping from a variable to some dummy value. It's actually not a dummy, it's like a black hole value. When we see it, it means bad things are happening. Now let's define the black hole. Cool. Then we use this body environment to evaluate the body. And then the next piece is, so when we evaluate the body, we have a value that the real value for this binding that we can use in the environment instead of this black hole. So we need to create a new environment and kind of patch our value. So this is how we are going to do it. So if the body is closure, then we need to create a new environment. And we also need to kind of patch our closure. But at least currently it is immutable, so we can't patch it easily. Well, let's make the environment mutable. If it's something other than a closure, we just return it as is. All right. So this looks good. Let's see if we can still run the Fibonacci. Yep, looks like we didn't break anything. So let's define the Fibonacci function in a direct fashion. All right, so we have a binding of Fibonacci to a lambda x, where we have a conditional, either one or false branch, which is the addition of Fibonacci x minus 1, Fibonacci x minus 2. All right, let's see if this actually works. Yes, it does. It works, and it also works, well, maybe not 3, but 2.5 times faster. That's very nice. And just to clarify, in terms of the debug builds, we went from 17 seconds to 1.4 seconds, which is more than 10 times the improvement. And again, this is not like super duper complicated code. Well, kind of this part is maybe a little bit mind-bending, but other than that, it's pretty straightforward. There is one thing though that we don't handle yet, and this is these bad recursive bindings. So if we actually let's create a program that does something like this. So basically it's let rec x. So let's see what happens when we actually run this. We can probably come in this. Yeah, so it returns black hole. Yeah, that's maybe not exactly what I was expecting. So maybe let's change this a little bit. Okay, how about now? Right, so we probably need to handle this exception. Yeah. Okay, cool. So basically when we try to add black hole to an int, we get a type error, and that's fine. But maybe what we would like to have is the a more specific error that says that, hey, we're trying to actually access an unevaluated name. So let's adjust the variable handling here. So what we can do, we can create another function that will check if something is a black hole. And then we need to use this function in our handling of variables. So basically we just something like this. All right, let's see if it's better now. Yep, so we get a very specific, well, a more specific error that we try to access an unevaluated name X. Cool, that's very good. And maybe just as a final bit. Let's see how this fares when we run it with the release flag in terms of performance. Wow, that's pretty good. So it's just 700 milliseconds to evaluate the Fibonacci of 30. Let's see if I have, just for fun, let's do the similar thing in GHC with Haskell. All right, so it looks like Haskell takes 2.7 seconds and a lot of memory to evaluate this thing. I guess that's a pretty good result. So how about Python? Do I have Python? No. Yes, I do have Python. Okay, so that was definitely faster. I actually don't know how to time the execution of Python code. Let's see if I can look something up. All right, so 10 invocations take 2 seconds, so it's about 200 milliseconds per invocation. So it's about 3.5 times faster than this. Anyhow, I think this looks pretty good. Cool. So to sum up, this is quite a bit better than I expected. The code is not much more complicated than it was with substitution-based term reduction, and in some ways it's actually simpler, and it is 10 times faster than what we had before, which is a pretty decent result. I was surprised that it is actually about 3 times faster than what GHC does in an interactive mode, and only 3.5 times slower than what Python does. Obviously, this applies only to this particular benchmark, which may not be representative of the overall performance, and probably it isn't. But still, it's an interesting thing that we get to this sort of performance numbers. What else? I think the important pieces introduced in this part are closures and the environment, and we will use them in the next part when we try to implement a bytecode compilation strategy, which means we will need to implement first bytecode generation and second the virtual machine. So that's gonna be a lot of fun, but for now, thanks for watching and see you later. Peace.